Hello, my name is Andy Schweitzer, and this is the first video in a series of electrochemistry videos. First of all, electrochemistry is simply the utilization of what's called a redox reaction, or an oxidation reduction reaction, and how we can apply these oxidation reduction reactions. Two ways that we can use a redox reaction, and then we'll eventually go in this video into looking what is a redox, but we can use chemistry to store energy. Okay, so in this case we're talking about a battery. All right, very critical piece of technology that when you look at a cordless drill, the actual mechanicals of the motor and the gears driving the drill are maybe 100 years old, but the battery pack is what separates it from one drill to another one. And then of course, so essentially we're going to use chemistry to store energy, and then reverse that around, we will use energy to run reactions. So just the reverse of this, we're using chemistry to store energy or energy to run chemistry. There are two reverse reactions. An example of this would be, a pretty common one would be what is referred to as electroplating. Very common in numerous amount of industry. Examples with everything from plating less expensive gold metals with more expensive ones. You can plate chrome on top of something like an iron. You can electroplate something to make it sterile. You can electroplate something to just give it aesthetically better looks. You can electroplate or a zinc coating on top of iron, which is called galvanizing, to prevent rusting. So there's all sorts of applications. Very important part of our industry in the United States today. Now, for the first question we ask here is, what is a redox reaction? And I'm really just gonna, this video is gonna just barely skim over the top of this. Not going to be something that we're going to spend a lot of time talking about. Just briefly describe what it is. A redox stands for the term oxidation and reduction. These two terms are pretty old. The original term for oxidation would be something that would gain oxygen. And a reduction would be something that would lose oxygen. These two terms technically still work. There's nothing wrong with it. It's just that over time we've learned more about the actual process, what's going on, and nowadays we've evolved the definition for oxidation reduction, but they have not changed the name of the actual process. Probably because the old definition still kind of works, doesn't encompass everything, it's just a small fraction. As a child growing up, I often heard about oxidation reduction reactions, and I said, okay, well, you hear about your car oxidizing, and you might also hear about, let's say, a fire as being oxidation. How can these two reactions both be oxidation? Well, if you take your car, which is predominantly iron, and when this thing reacts with oxygen gas, it will produce an iron oxide. There are a couple versions of it. Iron 3 oxide, for example, might be this one. And of course, carbon, a log burning, would be the oxidizing of a carbon molecule. Carbon plus oxygen to produce carbon dioxide. It will also oxidize the hydrogen as well. But either way, this is your standard combustion reaction, or part of it, and this is your standard oxidation of an iron, or rusting. Now, This one gives off a lot of energy, but in reality, happens a little slower, but also does give off energy. If you were to have a pile of iron, metal, cast iron per se, and it was in the dust form, and you were to put your hands close to it, you would definitely see that it gives off heat. In fact, your hand warmers are small packets containing just that, iron dust. You open them up, it's inside a little packet, expose it to air, it slowly oxidizes, evolving energy. And use that to keep your hands warm while you are at a Packer game or doing something outside when it might be cold. This one also would give off energy. Lots, maybe more, maybe it just runs faster. This one might just run slower. Amount of energy need to be evaluated closer. Either way, as we move on in this history of oxidation reduction, we have changed our definition to lose electrons, oxidize. All right, and to gain electrons, reduce. So in reality, these two things are linked by a transfer of electrons. Now, when I say transfer electrons, really I could also say transfer of charge. So in a redox reaction, you're going to be having a shift, or shift of charge, or a shift of electrons. Now, you cannot have one without the other. In order to have something to lose electrons, you must therefore have something to gain electrons. They have to happen together. I often refer to this like money. You could have $1 million. No one's willing to take it. You're in the middle of a desert or wherever. No one's going to take your money. Then it's useless. Same thing with oxidation reduction. One item needs to lose electrons. One item needs to gain electrons. So, how do we know? This is fairly important question. You must be able to identify an oxidation reduction reaction when you see one. How do I know if a reaction is a redox reaction? Okay. Now, to do this, scientists have developed what's called oxidation states. At some point, you can use these oxidation states to balance out your charge, but for the most part, it can be used to track charge. So, oxidation state is called the apparent charge on an atom. Okay, and how do we go about doing this, or how do we know what the apparent charge on an atom is? Okay, so there are a couple of rules, and what they do is they apply these rules to your reactants, and then they apply these same rules to your products, and then from there they can see, okay, based on the charges that are present in your reactants, and they'll see where those charges are present in your products, and they'll see, is there any change? Keep in mind, a chemical reaction is a rearrangement of atoms, and from the start to the end, those atoms particularly have the same charge. If they don't have the same charge, then one atom gave charge to another atom. Okay? Now, a couple of simple rules that you want to follow, and then I'll do some examples of basically showing you how to apply an atom with an oxidation state, or some people just call it charge. Now, here's a first rule that apply to both sides. Elements, okay, have no charge. I'm going to back up a second here. If you have an element and it doesn't have a charge, well then its entire oxidation state is just zero. So elements have no charge, and therefore their oxidation state is zero. Example, we could have, I don't know, Copper. Plain old copper has no charge, therefore its oxidation state is 0. Oxygen. Okay, there's two particles there. Each of them have a charge, but those charges equal. And since its elemental state is 0, well, then its oxidation state is 0 for each individual. If we were to have, let's say, lithium plus 1, now that's not considered the elemental form of lithium, plain old lithium. It's called lithium ion. And since it has a charge of plus 1, its oxidation state would be plus 1. This guy has an oxidation state of plus 1. We'll see more about that in a moment, but here we go. Ionic charges equal the oxidation states. Example of this, NaCl, plus 1, minus 1. These are also the oxidation states. If I were to go lithium sulfide, okay, just like I mentioned here, this would be a plus 1 and a minus 2. Those are also the oxidation states. Another one, which just to kind of clarify a few things, I think this is redundant from the previous one, but oxygen generally is a minus 2. It's one that we see quite often. So that has a negative 2 oxidation state. There is one exception to this thing, would be what's called a peroxide. And that is, a peroxide is any time you have an oxygen bound to another oxygen atom. That's by definition a peroxide. But in this case, it would be oxygen would therefore have a negative 1 oxidation state. Okay, and then hydrogen is generally going to be a plus 1. The exception to this rule would be a hydride. This is essentially where you have a metal and a hydrogen bound to that metal, and the metal acts as the cation. In this case, it would have a minus 1 oxidation state. Not real common. This peroxide is like hydrogen peroxide. That would be the most common form of, I would see, of a peroxide. Other ones rules we might have here is just so you're aware that all oxidation states equal, or I should say all the oxidation states add up to overall charge. An example might be in any ionic compound, for that matter. We would have AlCl3, aluminum chloride, plus 3, and minus 1. So 3 times a negative 1 is a minus 3, plus 3 on this side. Overall, it is going to equal 0. Okay, so these are our rules which we would go to apply an oxidation reduction reaction to. Now let's do examples of where you can assign oxidation states. This is something that's not very difficult. I'll use the rules from the previous page to show this. All right, so let's just say, for example, magnesium chloride. Okay, so plus 1 minus 1. Again, I goofed that up. It's plus 2 minus 1. Plus 2 minus 1. That one's done. We could say, for example, water, H2O. Oxygen's always minus 2. That's a rule, pretty hard, fast rule. And then the overall charge has to, this molecule does not have a charge. So the overall addition of all of these things has to equal 0. Has to equal 0. So hydrogen, of course, as the real state, is plus 1. Does that work? 2 times a positive 2. Right? This guy's now, whenever I'm assigning oxidation states, you have two layers of numbers. This is the important number right here. Okay, this is the actual oxidation state. And if you're doing a problem, this is the answer. Okay, right here. But I will above here give my overall, just so I can know what everything adds up to. So 2 times a positive 1 equals a positive 2. Positive 2 minus 2 equals 0. This is just for, you might say, office use only. And if I were on an AP exam, I would be careful about throwing these numbers up here without clearly identifying what my answer is. Okay. So 2 minus 2 plus 2 equals 0. Okay. Let's try another example. Okay, let's try nitrate. Now nitrate, NO3 minus 1, this thing has a -1 charge. So all of my overalls have to equal -1. The oxygen in this case is going to be a -2. There are 3 of them for a -6. And therefore this guy has to equal a +5 in order to get my -1. Therefore +5. These are my answers right here. +5 minus 2. That's the individual oxygen states of those individual atoms. We could try another one. Let's go with, let's say, MnO4 minus 1. Okay. In this case, manganese. It will be -2 for the oxygen. There's 4 of them for a -8. And in order to get a -1, this guy has to be a +7. This is my oxidation states right here. Manganese, I should say, will commonly break down into Mn+2. That's its most common point at some point when it wants to undergo a chemical reaction. Another example, okay, would be, let's say, chromate, CrO4 minus 2. This chromate and also dichromate, Cr2O7 minus 2, are commonly referred to as hexavalent chromiums, and we'll see why in a moment. They were the subject of a movie about starring Julia Roberts about cancer-causing chromium compounds, and it was quite a few years ago. But either way, they called them hexavalent chromium. Oxygen is -2, 4 of them for a -8. In order to get a -2, then this has to be a +6. And therefore, this here is my oxygen states. This would be -2, -14, +12 in order to get my -2. And therefore, there's 2 of them for a +6. Again, these are the reasons why these are called hexavalent chromiums. Chromium can be involved in some positive benefits, but it has to be chromium with a +3 charge, which is 3 electrons difference, but much different in chemical reactivity. How do I recognize, using these oxidation states, a chemical reaction that might be an oxidation-reduction reaction? First one here, I'll just write out a couple examples. Copper, metal, I'll put no charge plus, silver, nitrate, yields, copper, nitrate. This is a pretty simple chemical reaction, and plus silver metal. As I assign my oxidation states, this is going to be 0. This is +1. It's an ionic compound right here. So +1, and oxygen would be -2. The overall is 0 because there's no charge listed. So -2, -6, and therefore a +5 will get me what I want here. I'm going to back up one example. Well, I'll finish this up first here. This guy. Again, the nitrate's still the same, so technically the nitrate can be done together or separately. This thing splits here. This is a +2. The nitrate's a -1. Again, it doesn't matter how you go about doing it. The nitrate is the nitrate. You could do the whole thing together, or you could split the cation and the anion and do the nitrate separately like I did in the previous slide. I did just plain nitrate. Wouldn't matter, okay, how you want to do it. So in this case, we have the oxygen is a -2, -6. Therefore, this whole thing is going to give me a +5 in this case. This gives me a -1 charge. There's two of them for -2, and therefore giving me a net 0 charge. This guy is 0. So look at this chemical reaction. See, our charge is changing. I have my copper metal going to copper +2, and then I have my silver metal going to my silver ion to the silver metal. Okay. Now, this is definitely an oxidation reduction reaction because I have charges changing. The copper is going from copper metal to +2. In this case, the copper is going to be getting rid of 2 electrons, and this is called oxidation. Very important. Anytime electrons are on the product side is oxidation. You might say, well, shouldn't the electrons be on the other side? No. That is a very common mistake for students. Keep in mind, copper has a grand total of 29 protons. Okay, so I'm going to go 29 protons. It also, at this point, being neutral, has 29 electrons. This is a before snapshot. This is an after snapshot. They have to be the same. So now this copper still has 29 protons. But because it has a positive charge, it only has 27 electrons. There are the missing electrons that it lost. So this side has to equal this side. +2 -2 equals 0. They both can't lose electrons. If we have a loser, we must have a gainer. And this is going to gain 1 electron. Therefore, getting a little bit off topic, but this thing can happen twice. Because it loses 2, this guy only has to pick up 1. So this process can happen twice. Electron, whatever lost has to be gained. And it will loop together to form a balanced net ionic reaction of copper plus 2Ag plus yields 2Ag solid plus my copper ions. All right, so an example of a reaction that is not a redox reaction. All right. You also, if you were to track these combustion reactions, you definitely would see the charges would change as well. But here's an example which is not a redox reaction. AgNO3 plus NaCl yields AgCl plus NaNO3. Definitely chemical reaction. This will precipitate out as a solid. This will stay aqueous. This is a reaction that's purely based off of solubility. It's called a solubility reaction. Either way, ionic compounds, +1, +5, -2. Check it out. You'll see that this is a -6, so definitely balances to 0. +1, -1, +1, -1, +1, +5, -2. All the charges are the same. This is not a redox reaction. Thank you very much.